In this session, we will learn about parallel manipulator. So what is a parallel manipulator and why we prefer parallel manipulators over serial manipulator, and the various applications of parallel manipulator we will be discussing in this session. Parallel manipulator. In general, parallel manipulator is a closed loop kinematic chain mechanism. So what is a kinematic chain? So kinematic chain, it is nothing but it is an assembly of rigid bodies which are connected by joints in order to provide a constrained motion. So these links will be connected by joints, right? So the parallel manipulator, it is a closed loop kinematic chain mechanism. So as you see in this figure, so you have a fixed base and an end effector at the top. So each of the that is the base is linked to the end effector by different independent kinematic chains. A number of independent kinematic chains are used to connect the base to the end effector. Right, so each kinematic chain, it is, as you see, it has two links and they are connected by joints. Right. So the parallel manipulators, they will have either one loop or more than one loop. Right. And one more important thing to note is that not all the joints of the parallel manipulator are actuated. So the parallel manipulators, they do have some passive joints which are not actuated. Right. Next, we will see why we need to why we choose a parallel manipulator for our application. So here, as you see, you can see two tables. So they are the characteristics of the industrial manipulators. The first table is the characteristics of SCARA type manipulator, and the second table is the characteristics of spherical type manipulator. So as you see, for a spherical manipulator which is having 6 degrees of freedom, the load to mass ratio, it is less than um, 0.15. It is less than 0.15. So this that is therefore for a transporting mass of 500 kilogram, that is for a transported mass of 500 kilogram, the manipulator mass would be 3330 kilogram. Okay, so this is the manipulator mass. So when you say the load to mass ratio is 0.15, it means that for a transported mass or for a payload of 500 kilograms, the manipulator mass is 3330 kilograms. Now, when you just check the SCARA type of robots, so this ratio is generally better. So even in particular for the so-called direct drive robots, which doesn't have a reduction gear between the motors and the joints. So it is always in a SCARA type robots, especially the direct drive robots. It is the load to mass ratio is always less than 0.25 for heavy loads, which means that for the load capacity of the 500 kilogram, the manipulator mass would be 2000 kilograms. The manipulator mass would be 2000 kilograms. The second point that concerns the selection of parallel manipulator is the positioning accuracy. So the positioning accuracy for which there are two distinct concepts. The next important point is the positioning accuracy. So it depends upon two concepts, that is, one is the absolute accuracy and the other one is the repeatability. So the absolute accuracy, it is influenced by various other factors like internal sensors. So internal sensors we use to measure the joint position or to control the robot motion, we'll be using many internal sensors. So the accuracy is influenced by the internal sensor, then flexure of the links, flexure of links, then it is also influenced by the geometric realization, that is geometric realization. For example, the perpendicularity and parallelism of the successive rotational axis. We always prefer the perpendicularity and the parallelism in the successive rotational links. So these are the factors that influence the absolute accuracy. So in general, the absolute accuracy of a serial manipulator, it is very poor, right? So because as you know that we will be using the internal sensors. So if at all you have the internal sensor that uses that gives a erratic reading, that is if at all you have a sensor in order to measure the joint position and it is giving an error of say 0.06 degrees, right? The sensor is giving an error of 0.06 degrees, and this may lead to a erratic value in your end effector position, say about 1 m, right? So this errors they also get accumulated from one link to another, and so this is so hence we say that the absolute accuracy of a serial robot is poor, right? And also the next important thing is that where during the high velocity motions of the manipulator, it will experience several forces, that is inertial forces, Coriolis forces, centrifugal forces. These forces, they make the control of the robot even more complex, right? So this inertial forces, as we have seen in the earlier sessions also, they will vary with the square of the length of the link. So the inertial forces will vary with the square of the length of the link, and also the serial robots will be experiencing frictional forces, but the frictional forces are unaffected by the dimension. So we cannot design a serial robot simply by scaling down a larger version, right? So you cannot create a serial robot simply by scaling down the larger version. So when you just do the scaling down, the inertial forces are decreased, but the frictional forces remain unchanged, right? Though the inertial forces are decreased, the frictional forces remain unchanged. So therefore, we say that the serial robots are inappropriate for tasks which require either manipulation of heavy loads or good positioning accuracy, or to work at different scales. In these cases, we say that serial robots are inappropriate, and hence we prefer parallel robots. Another important concept is the compliance. Another important concept is the compliance of the robot. So when the end effector of a serial robot is submitted to some external forces or torque, there will be a slight change in the pose of the end effector due to the backlash in the driving flexure of the links. So this is not observed by the internal sensors. Therefore, they cannot be corrected. This we call it as passive compliance. So parallel manipulators, or generally the stiffness of the parallel manipulators are higher when compared to the serial manipulators, and so the deformations due to the passive compliance, they can be measured easily in case of the parallel manipulator. So this is an advantage of parallel manipulators over the serial manipulators. So we have seen the advantages of parallel manipulators when compared with the serial manipulators. That is, the parallel manipulator, they have better positioning accuracy, better load to mass ratio, right, high stiffness. But there are also certain drawbacks of in parallel manipulators when compared to serial manipulators. So the first one is that it has limited workspace, right? So you, as it is in a closed kinematic chain, so it has limited workspace because the legs, they will collide, and in addition each leg has 5 passive joints that each have their own mechanical limits, right? So the second point is that it will lose stiffness in the singular position. So if it is losing stiffness, it means that the robot will have infinite degrees of freedom, and then it may just be shaky, or it will move, right? So in that times it will be difficult to control. Now we will see the some examples of parallel robots. So the in the figure, what you see is a shake table that is developed by the Department of Civil Engineering of the University of Minnesota. This type of mechanisms, they were used when the first flight simulators were built. So the next example, as you see here, it is the Stuart platform, and the moving platform. You can see you have a tire attached. So in this moving platform, your tire is attached, and it is linked to the ground by using six links with varying length. So each you have six links here, and each link was of different length. So you have an universal joint at the one end of the link. You will have a universal joint, and a ball and socket joint at the other end. So by changing the length of the links, this will modify the position and orientation of the moving platform, and hence that of the wheel. Right. So this wheel, it is driven by a conveyor belt, and the mechanism will let the operator to measure the wear and tear of the tire under various conditions. And here you can see different applications of parallel manipulator. That is how a parallel manipulator is being used for tire testing, then micro positioning, manufacturing, and also even in robotic surgery. Right. So for precise positioning applications, we'll be using most commonly we'll be using parallel manipulators.